Welcome to Chemistry at Hanega High School. I'm Brian Brown, and today we'll be looking at Chapter 6, our first notes from Chapter 6. And Chapter 6 deals with the periodic table and periodic law. And first, what we're going to do is build kind of a history of where we got our periodic table from that you see hanging on the wall in chemistry classroom. Now, the first person of importance in terms of a periodic table was a French chemist by the name of Antoine Lavoisier. And in 1789, he published an early list of elemental substances. Now, there were only 33 elements on the list, far cry from the 118 or so that we've got in the periodic table now, and only 23 of them were actually elements. So here is what he published, and if you actually look at the breakdown, you'll see a number of things on here that weren't actually elemental substances. But it was a huge step forward because at this time, we were just starting to change our philosophy about science and chemistry and the world around us, and going from a to a particle view, basically, that had first come into play thousands of years before with Democritus. And John Dalton, who was the next person that came along, yes, this is the same John Dalton with atomic theory that we talked about earlier. Well, Lavoisier recognized the importance of elemental substances, and if we were looking at the particle nature of the world around us and understanding it better, it was important to understand that elemental things were important. Now, by 1808, when Dalton published his list, we were up to 36 elements, and all of the compounds were already taken from the list. So that early list gave scientists basically some things to try and break apart to see if they were truly elemental or not. Now, in Dalton's time, while we had a complete list without compounds in it, one of the things you'll notice is the symbols that were used at this point in time were picture symbols. And that basically dates, back probably thousands of years in some cases to some of the earliest representations of these elements. And they're very different from the symbols as we use them today, which is where Berzelius comes in. In 1814, he recognized the cumbersome nature of the picture way of doing things. So expanded the elements a little more. We now had 47 elemental substances. And he said, I think it would be more useful if we used letter symbols for elements on the periodic table. And while because of the names that were used from some of those elements changing and evolving, the symbols have changed somewhat on the periodic table. It's still a step in the right direction. So elemental things are important, and it would be more useful and easier and less cumbersome if we had letter symbols for them. Now, the next couple of scientists basically were doing the same thing. They were evolving an idea that was becoming more relevant as the number of elements grew. Because as we had this larger pool of elements, scientists started to make connections between them, and they started to recognize that there were things that were chemically similar. Now, what Dobereiner did was he classified elements into what he called triads. And triads were groups of three elements with similar chemical properties, and they had physical properties that varied in predictable ways within the triad. And the core of this idea is something that I don't think we would now consider scientific, but numerology and the importance of certain numbers in the world around us. Something like the number 3 in many cultures is a very, very important number. And he thought there was something magical and mystical about it, that elements would form in groups of 3. Well, it wasn't really important, the idea that there were triads, but what was important was he was making the connection that some elements were chemically similar to each other. And while the concept of 3 was a little bit ridiculous, even at this time, there were some elements that appeared to be similar to an existing triad. But for the very first time, we had scientists actively making connections between elements to group them together. And that's a huge step forward to getting to our modern periodic table. Now, along those same lines, John Newlands came along in 1864, and he wasn't looking at numerology. He was looking at another somewhat tenuous and tedious connection to the world around us, and that was through music. Many considered that music was this guiding principle through which math and science should have some reflection. And through his law of octaves, he was trying to impose the musical scale idea to elements. What he did was he organized the elements by increasing atomic masses, and he found that once again they were still in triads, so you'll see group of threes here, that there was a repeating characteristic or repeating chemical properties when you organize the elements from left to right, top to bottom, in what he called this law of octaves. So what he was seeing was this periodic repetition of chemical properties, which is really the heart of our modern periodic table. So he took the triad idea a step further, and rather than just having groups of three, they were connected groups of three. That when arranged by increasing atomic mass, you had things that were chemically similar to each other, like lithium, sodium, potassium, and so forth. Now, at the time, we had much more elemental things than the ones that are listed here. So this was an incomplete list, but he was starting to recognize the importance of not just chemically similar, but relationships between things that were chemically similar in a table form. Now, in 1869, we took a huge step forward when Dmitry Mendeleev published what we would consider one of the earliest periodic tables. Now, most people will credit Mendeleev with inventing the periodic table, but the reality is there was another scientist, Lothar Meyer, who did much the same thing at the same time frame. So it was really Mendeleev and Meyer that are credited really with inventing our modern periodic table. Now, the periodic table at this point in time had 63 elements, so the number of elements was steadily growing. He organized things that were chemically similar into rows. Shortly, he's going to change that to columns, which looks much more like our modern periodic table actually looks. And he organized them by increasing atomic mass. Now, one of the things he did that was critically important to scientists recognizing the value of this table was he recognized the fact that, we've been steadily finding more elements in the world around us. I think it's reasonable to assume that maybe there are some missing elements in our list of elements. So what scientists often tried to do when they were trying to organize elements is they would not leave room for the elements that hadn't been discovered yet. So they were looking for relationships and trying to come up with patterns within the elements that basically didn't work simply because of the fact that they weren't leaving room for the missing elements. And that was an important part of his table. When he put together his table by these guiding principles, there were some blanks. And he said, these are unknown elements that someday will be discovered. So you can see here his periodic table that was published at the time. So in the list right here, we have boron, aluminum, and then question mark. So really what he was saying was, after aluminum, it appears like there should be another element. We just haven't discovered it yet. So he predicted the existence of these unknown elements, like what he called eka aluminum, because it came after aluminum in his table. And based upon where it was at, he was able to come up with very, very good predictions for what these mysterious elements would look like, with their atomic mass, melting point, boiling point, their chemical reactivity, and so forth. And that gave scientists a clue to where to look to find some of these elements. And in 1875, French chemists discovered gallium, which is what Mendeleev called eka aluminum, and its properties were very close to what Mendeleev had predicted. And very quickly, scientists realized the importance and the relevance of the table expressed in this way. It wasn't just a list in alphabetical order of the elements, but it showed relationships and connections that had predictive powers for the different elements. Now, by 1871, he had now gone to the column format. And you can see across the top, he was organizing them by how they reacted in a similar way with oxygen. Now, we're almost to our modern periodic table at this point, but there was fundamentally something wrong with Mendeleev's table. And it wasn't wrong in many instances, but there were a few inconsistencies. And that was because he was organizing by increasing atomic mass, which by and large works, but isn't 100% accurate. And it wasn't until the science had developed for us to actually understand that different atoms had different nuclear charges. And in 1913, Henry Moseley proposed that we rearrange Mendeleev's table not by increasing atomic mass, but by increasing atomic number, which would be the nuclear charge on the atom. Later, we knew that was what we called the atomic number, and that stood for the number of protons. And at this point in time, we fundamentally have our modern periodic table. Now, there were still numerous elements to be added, but we fundamentally had the basic ideas behind how we build tables today. So if you take a quick review, which of these should you maybe be familiar with for what's coming up on the test? Well, one, Lavoisier's insistence that elemental things were important was a big step in the right direction. Berzelius's insistence that symbols were too cumbersome and we should use letters for our symbols was a big step in the right direction. And then Mendeleev himself, who came up with a table of similar chemical properties and increasing atomic mass. And then finally, to finish it off, Moseley going from increasing atomic mass to increasing atomic number. Those are really probably the four major scientists that you should be familiar with for Chapter 6 on the test related to our understanding of the periodic table. Now, the rest of these notes are going to be looking at the periodic table and how we group things and classify things on the table. So here's a look at our modern periodic table. And what we call a group or a family, remember, is a column on the table. So that would be the last column on the periodic table, which would represent what we're going to call the noble gases shortly. And then across that would be a period on the periodic table, and that's a row. And remember, the period tells you what the valence level is. What is your highest energy level? And the group is related to the number of valence electrons on that valence level. And also remember, there are 7 periods, and our F block here, remember, is actually in those, those 2 spots on that periodic table. So remember, we only have 7 periods. We don't have 9 because the F block comes after the 6s and the 7s on our periodic table. Now, what is a periodic table? Well, it's related to the concept of periodicity, which is a tendency to recur at regular intervals. And this goes back to the ideas of Newland's, where he was looking at the law of octaves, that periodic repetition of things coming back to the same part of the table were chemically similar. That's really the heart of periodic law when you add that to the idea of increasing atomic number. So in organized by increasing atomic number, there is a periodic repetition of chemical and physical properties. If that's true, then you are what we call a periodic table and you meet periodic law. So the table you see on the board in your chemistry classroom would meet periodic law, and that's why we call it a periodic table. It's organized left to right, top to bottom by increasing atomic number. And when you wrap around to a column on that table, you have things that are chemically similar together. Now, why is it they're chemically similar together? Well, honestly, we've actually already said this numerous times, so I don't think it's a big surprise that really what makes all of the elements in a group or family chemically similar is that they have the same number of valence electrons. So remember this first group over here, we call that the S1 column at one point. Well, those things are all things with one valence electron on the outside, and that makes them behave chemically in a very specific way. Whereas the boron column, so boron, aluminum on down, those would have three valence electrons, and that makes them behave in a chemically different way than those things that have 1 or 2 or 4 or 5 or 6 or 7 or even 8 valence electrons, which remember is our cap. Now, electrons then, and particularly valence electrons, control many of the chemical and physical properties of the atom. And that's why valence electrons are so critically important to our urine chemistry, is because how many valence electrons is going to control how you chemically behave, and it's also going to affect your physical properties as well. So when we look at the S and P block, and this is electron dots, which we did in the last chapter. It's the most simplified version of the electron configurations that we talked about. You would count across the S and P block. The first column in the S block would all have 1 dot. The second column in the S block would all have 2. Then we skip across the DNF, which we're fundamentally going to say all have 2. And when we get to our first P, we have 2 S's and 1 P, so we have 3 in boron, 4 in carbon, and so forth, all the way across the periodic table. Now, elements can be classified in a variety of different ways, and we're going to talk about a number of those ways today. One way would be to classify them based upon which block they're in, the SPDF thing. Now, a similar but different idea to that would be to come up with 4 categories based upon roughly what's happening in those 4 blocks. Now, the end of the P block is that one family of elements that's kind of all by itself in terms of the fact that it does something as a family that no other elements on the whole periodic table do, which is they don't react. They already have the right number of valence electrons, so they don't need to gain or lose any to become more stable. So the noble gases would be kind of a group all by themselves at the end of the periodic table, and that would be helium, neon, argon, krypton, xenon, and radon. And remember, they're characterized by a full valence level, a full S and P level. And in the case of helium, it doesn't have a P sublevel, so the full S sublevel. It's all that's on its valence. So these all have a full valence level. Now, many textbooks, and depends on which textbook you're looking at, will include the noble gases and the representative elements, which we do as well. So with the representative elements, we include the noble gases within the representative elements because these elements across the S and P block represent the full spectrum of chemical behavior. And a part of that spectrum is the non-reactivity of those noble gases. So the way we prefer to do it is to look at noble gases as a part of our representative elements, which would be our S and P block, really. Now, the first 7 of which within the representative elements would be things that have a partially filled S and P sublevel on its valence level, all the way up to the noble gases, which then have a filled sublevel. So we're going to include the noble gases, which is group 8A, in this distinction. So are the noble gases a representative element? We're going to say yes. Now, the remaining 2 classifications based upon electron configurations would really be the D and the F blocks. Another name for the D block is the transition metals. All of them are metals, and they're collectively known as transition metals. And they're characterized by a valence level with S electrons in it, and then you're now adding electrons into an inner D sublevel. And then finally, inside the transition metals, we have the inner transition metals, and that would be our F block. Because remember, that fits between the S and the D block. So in some ways, it's like it's inside the transition metals. And these are characterized by an outer level S electrons, and now we're putting electrons in an inner F sublevel. So one way to characterize is by SPDF block. Another way to characterize is by noble gas representative transition or inner transition. And when we look at that, remember, our blue would be our noble gases, and we're going to consider blue part of our red here, which is our representative elements, and then the D block transition metals, F block intertransition metals. So those are a couple of ways we can characterize or categorize things in the periodic table based upon electron configurations. Another very important way to classify elements is by properties, and this is something we're going to use significantly in upcoming chapters. So this is a really important type of classification. Many periodic tables, including the one I gave you, you'll notice boron, silicon on down, you'll see a set of stairs that have been drawn into the table. Well, those stairs separate our metals from our nonmetals. Metals are things that are collectively shiny, so they're lustrous would be the fancy name for that. They're malleable. You hit them with a hammer, they don't shatter, so they're not brittle. And they're ductile. You can pull them into a wire. And they're also collectively good conductors of heat and electricity. Everything to the left of the stair steps can be characterized by these fundamental properties. And really what ties them all together is they're very good at losing electrons. And the ability to lose electrons are what really give them most of these properties. Now, the opposite of metallic behavior would be non-metallic behavior. So these are in the upper right corner of the periodic table, to the right of the stair steps. And these would be dull-looking, brittle, and poor conductors. Now, we also have elements that are on the stairs. And remember, left would be metal, right would be non-metal. When you're on the stairs, you happen to have things that have properties of both. And we call those metalloids. So on the stairs minus aluminum, we have elements that are something like metals and something like nonmetals. So they might be shiny, but hit them with a hammer and they shatter rather than flatten out. And if you look at our periodic table, you can see where those stairs are that we're talking about. It's right in this area. All of the blue elements you see would be metals. The vast majority of the periodic table are metallic elements. Upper right-hand corner plus hydrogen would be our nonmetals, and those are shown in yellow here. And then on the stairs, remember minus the aluminum, we have our metalloids. Now, another way to categorize would be by family name. Some of these elements have been chemically similar, and we've been knowing they're chemically similar long before we had a periodic table or understood why they were chemically similar. So some of these names really predate our understanding of why they happen to be chemically similar. An example of that would be the noble or inert gases, the group 8A, or group 0 or group 18, depending on which type of numbering system you're looking at, the far right of the periodic table. That would be one important family, which isn't new because we've used this many times already in chemistry. Another important family would be to the far left side of the periodic table, where our alkali metals are. So this is group 1A minus hydrogen. Remember, hydrogen was a non-metal, so it doesn't fit in our alkali metals. Right next to them are alkaline earth metals, and the names are similar enough sometimes they're confusing. So remember this idea. The short one is the first. The longer name would be the second, alkaline earth. And that would be the group 2A or group 2. Now, how come they both share a similar part to their name, because that potentially makes it confusing? Well, it really deals with what the concept of alkali or alkaline means. Alkali or alkaline means basic. So when you put these elements in water, reactions occur which turn the water basic, hence the name alkali and alkaline earth. Now, the last family name of importance that we're going to talk about, and this is another one we're going to talk about and use quite a bit, would be the halogens, which would be group 7A or group 17. So just to the left of the noble gases on the far right side of the periodic table, we've got fluorine, chlorine, bromine, and iodine, and those would be our halogens, a really important non-metal group of reactive substances. Now, there's other columns on the periodic table, and yes, there are other things that have names. They're just not names that we think are important enough for you to memorize. So everything else we're just going to refer to by the element at the top of the family. So when we talk about the carbon family, we mean everything under carbon, which would be group 4A. So if it's one of the other elements, you just look at what the head of the family is to describe its name. And that ends our intro discussion into the periodic table.